Assalamualaikum and good morning. In this video, we're going to discuss about Laplace transform. Laplace transform normally symbol as S. Okay, when you see S, that means S domain, which is equivalent to Laplace domain. So why we need to transform our signal or system into Laplace? Okay, the answer for that is because after we transform from time domain into S domain, okay, either the signal or the transfer function of the system, then the analysis and controller design later on will be easier. So we can analyze easier in S domain rather than in time domain. Okay, so how are we going to transfer from time domain into S domain? Normally the symbol will be ft, that indicate function in time domain, small f, and then capital F here to indicate that the equivalent uh, of that function in S domain. So that's the symbol. And L here is indicate Laplace operator. We're going to apply the Laplace to this function so that we can transform that function into F. And the equation how to transform from T to S is given by this. So if you want to transform the function ft, then you have to multiply that ft with e a power of st. S indicate the Laplace domain, normally defined as this, which is a complex number. Okay, but don't worry about this because what we want here is just the symbol of s here. So multiply the function with a function of e a power of minus st, and then integrate that function, then you can get the Laplace equivalent of the function ft. Okay, so let's try with a simple function first. Okay, let's say you have unit impulse. Unit impulse, if you draw in time domain, is just like this, just one bar with a strength of 1. Okay, that's why we call it unit impulse. So unit, that means 1. So impulse with the strength of 1. So this is the unit impulse. So the symbol for unit impulse is delta. Okay, and then so if this is the function in time domain, so if you apply this, okay, that means you take the delta, multiply by e of power minus st, and then integrate this function. So integration, if you know, is the uh, area below the graph. So in this case, the area for this graph is just 1 here. So that means after you integrate delta function, you get 1. So it means this is the equivalent function for delta. In time domain, the symbol is delta like this. You know the graph is to be like that. And in S domain, the equivalent for delta t in S domain is equal to 1. Okay, let's try another one. Let's say now we have step. Okay, step function. You know the step function is like this. That means below 0 is 0. After 0 is constant at 1. Okay, or given by this equation. Okay, when t less than 0, the value of step function equal to 0. When t greater than 0, so the value is going to be 1. Okay, so if we apply the Laplace transform, okay, we take the function which is 1. Okay, because we only interested between 0 to infinity. So between time 0 to infinity, that means ut equal to 1. Okay, so 1 multiplied by e of power minus st, and then you integrate that within this range of 0 to infinity. So when you integrate this, okay, remember this one, when you integrate, you get minus 1 divided by s multiplied by the original function. Okay, and then you take the limit from 0 to infinity. Okay, so if you substitute the value here, okay, the value of s here, you have not s, t. Okay, you substitute the value of t here. Okay, if t equal to infinity, when t equal to infinity, e of power of minus infinity will be equal to 0. Okay, and then if we substitute t equal to 0, e a power of 0 equal to 1. So you multiply with this, you should end up with 1 over s. So this is the equivalent function in s domain for unit step. In time domain, unit step equal to 1, okay, and in s domain will be equal to 1 over s. Okay, let's try another one. Okay, exponential function. Let's say you have this exponential function, okay, because the power here is negative, that means is instead of going up, so it's going down like this. It's a decay function, because when you substitute t equal to 0, then this value equal to 1. So that means it start at 1, and then as the value of t increase, the value will become smaller and smaller until it's saturated somewhere near to infinity, which is very close to 0. Okay, so let's start the function. So you have this function, multiply with the e of power minus st, or you can group this together to become like this, s plus a multiplied by t. Okay, and then you integrate this function. When you integrate this function, okay, you get minus 1 divided by s plus a, the term inside here, and multiply this function again. Okay, and then you take the limit from 0 to infinity. Okay, substitute the value of t. Again, when you have t equal to infinity, everything become 0 here. Okay, when you have uh, 0 there, okay, everything become 1. So as a result, you're going to have 1 divided by s plus a. So that means this is the equivalent in s domain for this function of e of power of minus 80. Okay, let's try another one. Okay, this is ramp function. Okay, a multiply by the t. A is just a constant or scalar that you multiply with the t. Okay, so a doesn't change whether in time domain or s domain, just the same value, because it is just a constant. That means if you translate this into a ramp function, this is the ramp function. Okay, the ramp function, so a is just the slope of this line. Okay, so how are we going to get this value? Okay, so you just apply this. Okay, integration of a 18, this function multiplied by e of st. Okay, and then you do the integration. Okay, if you forget about that integration, you're supposed to use hang on, let me show you. You're supposed to use the table of integration. Yeah, you're supposed to use this formula of integration. So if you forget already, so do your revision about integration. So you should use this formula in order for you to integrate this, and you're supposed to get this, and then substitute the value at the end, you're supposed to get this. Okay, so probably by now you notice that um, the case become complex. Okay, the integration become more and more complex as you have more and more complex function. Okay, but don't worry, because we're not going to use this integration. Okay, we're not going to integrate this all the time, but instead we're going to use the Laplace table. So look at this table. So if you have the list of table like this is the function for delta just now we just derived, equal to 1 in s domain, step function equal to 1 over s, ramp function equal to 1 over s squared, and so on. We prove that this we already proved equal to 1 over sa. Okay, and you can also prove that sine omega t will be equal to this, and cos omega t equal to that. So you can do the integration and then start to produce this table, but you don't have to do that because it's already done by previous engineer or mathematician. So we just use the table. So now how are we going to utilize the table? Okay, before that uh, I want to explain this. Okay, TUT. So TUT, sometimes we just write ST, because in control system we do not interest about the value before 0. Negative time, you do not interested about negative time. Everything we start from 0. Okay, so that's why the RAM here you multiply by a step function, so that any value before 0 we're going to neglect, because we already multiply by step function. Step function start at 0. Okay, so that means if even if I write t, that means this t multiplied by ut. Similarly for this and all this, for example, in this case you have cos omega t multiplied by ut. So actually cos omega t only, because multiplied by ut just to indicate that we want to disregard the value before 0. Okay, so cos omega t will be equal to this, s divided by s squared plus omega squared. Okay, that's some portion of Laplace table. So we're going to have a complete Laplace table. Um, you know, oh, it's here. Okay, complete Laplace table like this. Okay, so you have here so many Laplace. So this is the time domain, this is Laplace equivalent. You can get this from the textbooks or from website. Okay, there are so many functions that has been derived to us by our mathematician or engineer before this, so that we have a long list of table like this that we can use in our analysis and design, um, how to transform from time domain to Laplace domain. But the procedure is as we discussed just now. Okay, that's how they did it last time. Okay, so before we can utilize this Laplace table, so we need to learn also about the theorem of Laplace transform. So that means how we're going to use the table effectively and easily. Okay, so the first rule, of course, is just definition that we discussed just now. The second theorem is called linearity theorem. So if you have the function in time domain like this, function of t multiplied by k, a constant, okay, in time domain, you just transform the ft and then the k, you just multiply. Okay, let me give you an example for that. Um, so I'll make it smaller. Okay, let's see this. Okay, let's say we have the function f1 here equal to 5 ut. So you probably recognize that ut is a step function. So step function in Laplace domain is from the table is equal to 1 over s. Okay, so you take 1 over s. So according to this formula, so you take 1 over s, just multiply by k, you get the Laplace equivalent for that. So similarly in this case, so you have k equal to 5, so you take ut, transform that into Laplace, which is 1 over s, you can refer to the table, and then just multiply by 5 here. So this is the Laplace equivalent for this. So let's say you have another function f2 equal to 7 tut. So tut, you know that this is the ramp function limited by the step function. Okay, so ramp function, if you refer to Laplace table, is 1 over s squared. So if you have the multiplier here, just carry over to s domain to become like this. So that's the first theorem. The second theorem also belongs to linearity theorem. It says that if you have two functions like this, if you want to transform into Laplace, you can do individually. That means if you transform f1 to be the small f1 here to become a capital F1 here, and then transform this individually into its equivalent S domain. So if you transform this, is equivalent to take the individual Laplace transform, just add them together. Okay, for example, in this case, if the function one is a step, the second one is the ramp. So if you transform, if you look at the table, the step, if you want to transform like this, so the step will be 1 over s, and for the ramp function will be equal to 1 divided by s squared. So we just write like this in s domain. So there's a linear theorem number 2. Okay, the next one is the frequency shift theorem. When you see something like this, S plus A in S domain, that means it's frequency shift theorem. Okay. What is the theorem? The theorem says if you have a function in time domain and that function is multiplied by another exponential function like this, okay, if you want to transform that into Laplace, you just take the original function and then at the place of s, you just add s, you replace with s plus a power of this, which is in this case a. So you have fs plus a. So for example, in this case, okay, let's say you have this function ut, step function again, multiply by this, okay, exponential function. So you know that this is in time domain is just 1 over s, okay, just 1 over s, 1 over s. So at the place of s, you replace this with s plus the power of this, which is in this case equal to 2. So the equivalent Laplace transform for this is equal to 1 divided by s plus 2. Let's try another one. Let's say you have e of power of minus 5t multiplied by the ramp function. So you know that ramp function in Laplace domain is 1 over s squared. So you replace this s equal to s plus the power of this, which is now equal to 5. So s plus 5 square, okay, because you have square there. So this is the Laplace equivalent for this. Okay, and then time shift theorem. Time shift theorem, that means you see plus or minus in time domain instead of just now in s domain. Okay, time shift, the plus or minus must be in time domain. Okay, if you have a function like this, then the Laplace equivalent will be e of power of minus st. Okay, and t here is the time here, the time lag here, equal to t. Observe the symbol. If you have minus here, minus there. If you have plus here, then plus there. Okay, and then multiply by the original function for Laplace equivalent for that ft function. Okay, let's see the example. Okay, let's say you have the step function now delay by 3. Then if you plot the graph, the step function start at the time of 3 instead of time of 0. Okay, so what is the Laplace equivalent for that? So according to the theory, say you just take the step function, okay, in this case step function transform that into Laplace. So step function is 1 over s, and then in front you just multiply by e or power of this minus 3s. Okay, just like this. Okay, let's try another one. Let's say you delay, and now you have the ramp function but delay by 2. That means the ramp function instead of starting at 0, now it start at 2. Okay, so ramp function is 1 over s squared. So delay by 2. So e of power of minus 2s. Okay, that's how we use this time shift theorem. Okay, the next one is scaling theorem. Okay, this scaling theorem. So it's different from this because this one is k is outside the function, but in this case, the a is together with the t. Okay, so it's different cases. This one is k constant is outside this t domain. Okay, t operator, but in this case is inside. Okay, inside the bracket. Okay, so if you have something like this, it's called scaling theorem. So how we're going to transform that into Laplace domain? So the first step is at the place of s, before that you put s divided by a. Okay, and then outside you multiply by 1 over this a. Okay, let's see the example. Um, do I have it? Yeah, this one. Okay, let's say you have this u 2t. Okay, we know that u is a step function. So step is in s domain is 1 over s, but instead of s, you replace the s with s divided by this number, which is in this case s divided by 2. And then don't forget to multiply outside 1 over 2. Okay, these two. Okay, let's try another one. Tu 4t. So that means this is the ramp function, but the time now is 4t. Okay, so the ramp function, you know that is 1 over s squared, but instead of s, you replace that s with s divided by 4 and then squared. Okay, and outside you multiply 1 divided by 4. Okay, the next one is a differentiation theorem. Okay, if you have the differentiation like this of a function, so what you need to do in Laplace is just find that function, the f function, put it there and multiply by s. If you have one differential, 1s. If you have 2, you have 2s. You have n, then s a power of n multiplied by that function. And don't forget to minus the initial value of this time domain function, minus the initial value. So if you have s squared minus the sf of that function, initial value for the first derivative of that, minus this one is the real initial value, and also minus the first derivative initial value, and so on if you have higher value like that. But don't worry, because in control system, as I said just now, we always starting our analysis starting from 0. So most of the time, this value will be equal to 0. Okay, and if it is not 0, then it will be given to you, or you can always assume equal to 0. The result will be not so affected. Okay, we will see later on in the example when we have this value of initial uh, function. Okay, but the main idea is you have one differential there, you put one s multiplied by that function. You have double differentiation, s squared. You have n differential, s above n multiplied by that. Okay, let's see one example here. Let's say you have the step function. You want to know the Laplace of that step function that has been differentiate once. Okay, so according to this theorem said, so you transform the function into s domain, ut you know is 1 over s. Okay, and then because you differentiate once, multiply by s, 1s outside. When you multiply, and of course you have to minus the value of initial value of u in time domain. Okay, I forgot to explain this. 0 minus. Okay, in this case also indicate 0 minus, 0 minus, 0 minus there. 0 minus, that means the value immediately before 0. Okay, 0 plus is value very close to 0, but on the plus side. Here we have 0 minus, that means the value very close to 0 on the minus side, on the left side when we approach the uh, starting of that function. That means it will represent the step in this case on the left hand side, which is 0. So 0 minus equal to 0, 0 plus for step function will be equal to 1, because step function after 1 after 0 after t equal to 0, the output of a step function is equal to 1. So 0 minus is 0. Okay, 0 plus is equal to 1 for step. Okay, so when you multiply this, you get 1. Of course, this will be equal to 0, so you get 1 for step function. Okay, let's try another one. Let's say you have the ramp function, you differentiate the ramp function once. So the ramp function in s domain is 1 over s squared. So you differentiate once, you multiply by 1s. And of course, you have to minus all the initial value. Okay, here the initial value for ramp function, because you multiply by this, so starting at 0. So initial value equal to 0. So you multiply this, you get 1 over s. Okay, let's say now we differentiate twice. Okay, you have step function. You have step function, you differentiate twice, so that means you have to multiply by s squared. So step function is 1 over s. So you have, because you differentiate twice, don't forget you have to minus two initial value. The first initial value is for this one, okay, this one s f1. So that means this is the initial value of the function, original function f multiplied by s. Okay, this is what you get here, original initial value multiplied by s, and minus original function in time domain appreciate once, and what is the initial value for that. Okay, initial value for that. But in this case, initial value is equal to 0 for the first one. So is the first one equal to 0? Normally the second one also equal to 0. Okay, so in this case, you will end up will be equal to s only. Okay, that's how you apply this function. But as I said just now, the main idea here is you multiply by the s when you have integration, you have differentiation. Okay, so integration theorem. So integration theorem. So if you have the integration of the function t in time domain, in s domain, you just write that function divide by s. You integrate once, you divide by 1s. If you integrate twice, you divide by s a power of 2, and so on. So let's try the example. Let's say here you have ut. You integrate that function. So in time domain, in s domain will be original function for that. Ut is equal to 1 over s. So you integrate once, divide by s. So you end up with 1 divided by s squared. Okay, nothing special, just divide by s. So if you integrate twice, then divide by s squared here. Okay, another two theorem which is very beneficial when we want to analyze the performance of the system, or the end value or final value of the function. Okay, look at this final value theorem. Final value theorem, of course, these two, the final value theorem required that the signal is converged. If the signal is not converged, so probably it's not going to give you good result or correct result. And the function should also be continuous at time equal to t. At t equal to 0. Okay, but as you can see in analysis later on, even the value is not infinity, also it is not a converge, also it can give the correct value. Okay, let's try this final value theorem. Final value theorem, that means we want to know what is the value of the function in time domain at when time is infinity. Okay, so in Laplace domain, as I say, is very easy. That's why we need the Laplace domain. If you want to know the final value of the function in time domain, you can check using Laplace like this. You take the Laplace equivalent of that function, multiply with the s, and then set the limit approaching 0, and you're going to get the final value. Okay, let's see this example. So you take Laplace of u. Okay, u is a step function. Okay, and then the Laplace equivalent of step function is 1 over s. So you multiply with the s. Okay, multiply with the s and set the limit to 0. Okay, when you multiply this, of course you get 1. So there's no need to set the limit equal to 0. It's already become a constant equal to 0. Okay, let's check. This is the step. So at the end here, of course, you get 1. Step always 1, even though the time is infinity. Okay, so that's proof that this theorem, final value theorem, is correct. Let's try the ramp function. Okay, let's say you have the ramp function like this. The ramp in s domain is 1 over s squared. So you multiply with the s. Okay, you get 1 over s squared, and then you set the limit to 0. Okay, if s approaching 0, so 1 over 0, this value, this function will be approaching infinity. 1 over 0 is infinity. So you check here the ramp function at the time of infinity. Of course, the value grow to become very high, so it's going to approach infinity. So this is the function that we know. Let's say the function is complex, we cannot draw or we cannot imagine, but you don't have to worry, because you have this theorem. You just apply this theorem to Laplace equivalent of that function, then you'll know the final value of the system or of the function. Okay, initial value theorem. So initial value theorem is the theorem that we want to check the starting of the function. Okay, in this case, look at this is 0 plus now. So that means the value of that function immediately after 0. Okay, so the theorem say if you want to know the initial value theorem, initial value of the function t, so you take the Laplace of that equivalent function, multiply with the s, but now you set the limit to infinity. Then you get the value. Okay, let's see the example. Okay, let's say we take the step again. Okay, step function again. So we set the limit. Step function we know 1 over s multiplied by s. Okay, multiply by s and set the limit to 0. But of course, for step function after you multiply, it's become 1 already. So no need to apply this limit. So it's equal to 1. Yes, so the step function after the 0 is equal to 1. So it's true. Okay, let's start the ramp function. So the ramp function is 1 over s squared in Laplace domain, multiply with the s, so you get 1 over s. So now you apply limit to infinity. So 1 over infinity will be equal to 0. So if you look at this, of course, the initial value here is 0. Okay, that's how you apply this initial value theorem. So how complex is the function or signal? It doesn't matter, but if you know the Laplace equivalent for that signal or function, then you can check the value of the initial value of that function. Okay, so I think that's all for this video. The next video we're going to discuss about the inverse Laplace transform.